Welcome to Chapter 16. We're going to talk about oscillatory motion and waves. So things that exhibit oscillatory motion are springs that are allowed to expand and compress due to a weight, maybe a simple pendulum, a water wave, sound waves, all kinds of things out there show some sort of a repetitive motion if left to their own devices. So we'll start out with the easiest one, which is the simple pendulum. It's sometimes, its motion is described as being simple harmonic motion. And so when you displace it, we'll scroll down just a tad so we can see the drawing. So in the equilibrium position, the blue pendulum bob would just hang straight down. If you pull it off to the side, it would be in the far right position. If we let it go, it'll swing down and over and then come back. Down and over and then come back. So one complete period would be, it starts pulled way to the right, goes all the way down and over and comes back to its starting position. That would be one period, the time it takes for the pendulum bob to be released and return to its starting position. All right. The the period is capitalized by, symbolized by a capital T. Period is going to be symbolized by capital T. And for a simple pendulum, it's equal to 2 pi multiplied by the square root of L over G, where L is the length of your pendulum string, and little g is the acceleration due to gravity wherever you are. So if you're at sea level, little g would be 9.8 meters per second squared. If you're on the top of Mount Everest, it'll be a little less than that. If you're on the moon, it will be much less than that. So little g varies with location. So you can have a pendulum and take it to different places, and its period will be different. It's important to notice that the period is independent of the amplitude, so it doesn't really matter if you pull the pendulum bob out a little or if we came way up here and pulled it out a lot, the period would be the same. And it doesn't matter how heavy the bob is on the end of the pendulum, as long as we can ignore air resistance. So it's dependent only on the length. T equals 2 pi times the square root of L over G. All right. So where do you see these? Well, you see them in grandfather clocks. My grandmother had a grandfather clock in her living room. I actually don't have any friends that own one, but maybe you do. So a grandfather clock has a pendulum. Usually it's on a rod, not on a string, and it moves slightly right and left, and that's how the clock regulates itself. If your clock is running slow, you need to speed it up. So you want the pendulum to swing a little faster. To make the pendulum go faster, you want to have a smaller period. T should be a smaller number. And the way to make T smaller is to make L smaller. And so what you would do if your grandfather clock is running slow, you'd have to raise the weight attached to the end of the pendulum arm. All right, let's look at some other examples. Let's look at one where we want to use the period to figure out the acceleration due to gravity on a mystery planet. So we're on our mystery planet, and we know the period is 10 seconds. We know that our string is 2 meters long, and we will be able to use that to figure out what's little g on our planet. So capital T, which is the period, is 10 seconds. Capital L is the length of our string, 2 meters. We're looking for a little g on the planet. And we know that T equals 2 pi times the square root of L divided by G. So it's a simple matter of plugging in. So we write down our formula, T equals 2 pi times the square root of L over G. And then we plug in. I'm not quite sure why. Whoops, it won't let me move it over. Okay. I was hoping, oh, there it goes. I like them lined up. All righty. So we plug in. T is 10 seconds, L is 2 meters, pi is just pi, and little g is what we're trying to solve for. All righty. So we have 10 seconds equals. We want to get the g out of the denominator, but we can't get that until we have the radical all by itself. So the first thing we want to do is divide both sides by 2 pi. So 10 seconds divided by 2 pi will equal the square root of 2 meters divided by g. 2 meters divided by g. So 10 seconds, pi is 3.14, so 2 times 3.14 would be 6.28. 10 divided by 6.28 should give you 1.59 seconds. If you don't get that, ask me for help. So 1.59 seconds equals the square root of 2 meters divided by g. What we need to do is get rid of the radical sign, the square root sign, and so to do that, you square both sides. We square both sides. So 1.59 seconds squared will equal, on the right-hand side, if you square the square root, the radical sign goes away, and we're just left with 2 meters divided by little g. So 1.59 seconds, if we square that, we get 2.53 seconds squared. So 2.53 seconds squared is equal to 2 meters divided by g. We need to clear the denominator, so we multiply both sides by little g. And it's important to remember right now, little g is not 9.8 meters per second squared. Little g is what we're solving for. So we've got little g out of the denominator, but now we need to get little g all by itself, which means we divide both sides by 2.53 seconds squared. So little g is going to equal 2 meters divided by 2.53 seconds squared. And when you do the arithmetic, you end up with little g is equal to 0.79 meters per second squared. There are some problems in your study guide, so you want to be sure to look at them. I will expect you to know the formula and how to use it. All right, let's talk about forced vibrations and resonance. So all vibrating systems or objects have a natural vibrating frequency called the resonant frequency. When you push or energize something at its natural resonant frequency, you're going to enhance the vibration. All right? And everything has a natural resonating frequency. Probably the example we're all familiar with is pushing someone on a swing. If you push someone on a swing at the right point in the cycle, which would be when the child is all the way back and they've momentarily stopped to change directions to go forward, that's when you push. And if you push, then just a little bit of added energy on your part will make them swing higher and higher and higher. If you push at the wrong place in the cycle, suppose you're impatient and the child is swinging back, 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 and you push right about here before they've gotten all the way back to where they will change directions. If you push too soon, you're going to screw it up. If you push too late, you're going to screw it up. So it has to be in sync or in cycle with the natural resonating frequency of the child in the swing. There are other ways in the world that we can show resonance. We have tuning forks that are mounted on wooden boxes, and the two tuning forks are the same natural frequency. If I hit one of them, the sound waves from the first one will actually cause the second one to vibrate. We had a little dog who was very yippy, and I had a wind chime hanging in my kitchen because I liked it there. And so one day I was listening and I heard a noise and I couldn't figure out what it was. It was really high pitched. And then I went into the kitchen and figured it out. The dog had yipped at the exact same frequency as one of the pipes on my wind chime. And her little yip, yip, yip had started one of the pipes to vibrating naturally. And so when she stopped barking at a squirrel or a leaf or whatever it was, the wind chime was still vibrating just a little bit, and I could hear it because her bark and the frequency of the wind chime were the same frequency. She had set it into resonance, into sympathetic vibrations. A singer and a crystal glass is another example of this. Enrico Caruso, who was an opera singer back in the early 1900s, was famous for being able to take a really thin wine glass and hit just the right note to make the wine glass not only vibrate but shatter. So he could make it break. There are all kinds of popular and the reason, of course, was because the note he could sustain and the natural frequency that the wine glass vibrates at were the same frequency. It wouldn't have worked if he hadn't hit the same frequency as the wine glass. There is a video, there are lots of videos on YouTube about a young man breaking wine glass, actually, yeah, I guess it's a wine glass, with his voice. I will put the link in the chapter assignment, but you really ought to watch it. It's really tremendous. And he's so excited about it. Another example of resonance is the oops, this is number 4, isn't it? Because the wine glass was 3. Yep, this is number 4. So we've got the Tacoma Narrows Bridge. So in Tacoma, Washington, there's an area noted for its wind, the Tacoma Narrows, and there was a bridge that was built. This bridge had a long center span. So between support and support, you can see it's a suspension bridge. Between the two supports, it was very long and very narrow. It wasn't very wide. And there was a steady wind in the Narrows. Well, the wind happened to be at just the same frequency as the natural vibrating frequency for this part of the bridge. So the wind would blow and the bridge would vibrate. In fact, the bridge was given a nickname, Galloping Gertie, because as you would drive along it, they said that cars in front of you would disappear from view because of the vibrations set up on the bridge, that it would cause the bridge to undulate. Well, one day, not too long after the bridge had opened, the winds blew and it was persistent. It kept blowing and blowing and blowing. And so the bridge began to vibrate and vibrate. And you can see a little snippet here where the bridge is vibrating. It vibrated so much that the bridge actually collapsed. There's a video link right here, which again, I'll put in the chapter so you can click on it. They had in place a plan to stop the vibrations. They just didn't get to implement it. What they were going to do is take supports from the pillars out to sections of the bridge to brace it. So they would come from the pillar out to the bridge, and then over here from the pillar out to the bridge. And what that would effectively do is reduce the length of the unsupported span, and that would change its natural vibrating frequency. But they didn't get it done before the bridge collapsed. They have rebuilt the bridge, but not in this exact same spot. All right, wave motion. Waves transport energy from one location to another by vibrating the molecules of the medium. So like one water molecule bumps into another water molecule and the energy moves along. So a single frequency continuous wave would look like this. So molecules might come up and come down and come up and come down and come up and come down. Wavelength is from similar point to similar point on a wavefront. So maybe top point to top point. The top points are called the crests, or it could be from low point to low point. The low points are called the troughs. Or it could be from halfway up a crest to halfway up the next crest. The wavelength and amplitude is how high above the equilibrium position would it be. So you have amplitude and wavelength. So the amplitude is the maximum displacement. We symbolize it by capital A, and it's measured in meters. Wavelength is the horizontal distance between two similar points on a wavefront, and it's symbolized by the Greek letter lambda. I notice this one has a lot of curly loops on it. You don't have to do the curly loops. It looks like an upside down Y. So let's do a drawing, because again, I've seen some terrible, I think I can do it with a line. All right, so it is, you draw a little short line down, and then you draw a long line coming across. So short line down, long line coming across. Do the short piece first and then the long line. The whole thing probably takes up the same size as a capital letter would. But the little cross piece that comes down that you start with would start about at the middle of the line. And again, you don't need those little loops. So it's two lines, a short one down and then a long one coming to connect. That's your lambda. Let's get that out of the page. All righty. So wave velocity is measured in meters per second, and it's symbolized by lowercase v, v for velocity. Velocity is related to frequency and wavelength by this equation, v equals lambda f. V equals lambda f. Little v equals lambda multiplied by f. V is in meters per second, lambda is in meters, and f is in hertz or cycles per second. Excuse me. All righty. So the velocity of the wave depends on the medium. Obviously, you could set up a wave in a piece of rope, and it would be different than a wave set up in a garden hose or set up in a piece of string. It would all vary. Or if we're talking waves in a fluid, it would be different in water compared to syrup, compared to semi-congealed jello. We have different types of waves, two types. We have transverse and longitudinal waves. A transverse wave, the particle displacement is perpendicular to the wave motion. So it looks like a snapped rope or a water wave. Particle displacement goes up and down, wave motion goes side to side. All right, transverse wave. They have crests and troughs. So a crest is the high point, a trough is the low point. Remember, wavelength would be from like point to like point, so maybe crest to crest. And amplitude is how high are you above the equilibrium position. A longitudinal wave, the particle displacement is parallel to the wave motion. This would be like compressing a spring or a slinky. So the wave is moving to the right and the particles are compressed in that same direction. Wavelength is from similar spot to similar spot, and we don't have crests and troughs for a longitudinal wave. We have compressions and expansions, which used to be called rarefactions. Expansion is a more common term now. So particle displacement is back and forth, wave motion is in that same direction. And again, a compression and an expansion. Compression, expansion. You'd see the term rarefaction in older books. And let's see, let's talk about the behavior of waves. So waves undergo reflection. When a wave strikes an obstacle, it bounces off. So if the solid blue line is our obstacle and the dashed line perpendicular to it is the normal to the surface. What's the normal to the surface? It's an imaginary line drawn at 90 degrees to the surface. angle of incidence is going to equal angle of reflection. So if the wave comes in on the left, strikes the surface and bounces off, the angle of incidence will be from the normal to the incoming wave, and angle of reflection will be from the normal to the outgoing wave. So comes in, goes out, angle of incidence is the angle on the left, angle of reflection is the angle on the right. Angle of incidence equals angle of reflection. Waves also undergo refraction. That's where they bend as they pass from one medium or material into another. So maybe we've got going from air into water. Again, the dashed line is the normal to the surface. And again, you would measure with respect to that normal. So theta 1 would be the big angle in air, and theta 2 would be that smaller angle down in water. So the law of refraction just relates the angle, the signs of the angles to the velocity of the wave in the medium. We'll do more of this in the second semester when we use it for optics. But for now, it's important for you to know that refraction is the bending of a wave as it moves from one medium or one material into another. Interference and superposition. So you have two waves. They can be in phase or out of phase, and we'll talk about those in just a minute. And then we have diffraction. That's the bending of a wave around an obstacle. So the amount of diffraction depends on the wavelength and the obstacle size. And again, we'll do a little more with this in the second semester as well, but let's look at the photograph. So this is an overhead view of water waves. Here are some rocks, and you can see the waves bending. So if the waves are coming in from the bottom of the photograph, when they strike, the rocks don't stop the wave, and there's not just empty space on the other side, but the waves actually bend around. And in fact, in the bending process, they go from being relatively straight to curved. And we'll talk about this again in the second semester of the course as well. So let's talk about phase and interference. When you had trig at some point in time, you might have had a unit circle where 0 was on the horizontal axis, 90 was straight up, 180 was off to the side, 270 is at the bottom, and 360 we've completed our circle. If you didn't, don't worry a lot about it. We take the unit circle and sort of unfold it and make a sine wave out of it. So 0 is where we start, 90 is when it goes up to a crest, 180 is when it comes back to 0, 270 is down in a trough, and 360 would be back at the horizontal axis. Two waves are in phase with each other if they match up. So if we have our first wave drawn like a standard sine wave, and our second wave to be in phase with it has to be drawn the same way. So in phase, they match up. You can see that 90 degrees on our original drawing was up at a crest. So to draw something 90 degrees out of phase with our first drawing, so here's our first drawing, 90 degrees out of phase would mean the second wave would have to start at a crest. And it does in this picture. So these two waves are 90 degrees out of phase with each other. To be 180 degrees out of phase, 180 was we've gone all the way up and we've come down. So it would be at the horizontal line going down into a trough. So for 180 degrees out of phase, one wave comes up and then goes down. The other one starts down and then goes up. So they're opposites. 180 degrees out of phase, they've exactly flipped when compared to each other. 270 was down here at the trough. So to be 270 degrees out of phase with our standard wave, we would have to start the second one down at a trough, and you can see that's exactly what we did. Let's look at interference and superposition. So when two waves meet, You can have all kinds of different interference. We can have constructive interference. So they have to have the same frequency and they meet in phase. They have different amplitudes sometimes, but the same frequency, they meet in phase. And the result is you get a resultant wave that has a larger amplitude than either of the others. They add. It's a simple process of addition. And the little chart is meant to show you that. So the first one would be X's go across the horizontal axis, Y's go up and down. The first wave is for the Y1s, the second is for the Y2s. It's enough to know that if they're in phase, then they're going to add and you get constructive interference. So if you could just recognize that these two are in phase, it'll give us constructive interference. And that means that our resultant is going to look bigger. So they start out at 0, but if this one's at 1 and that one's at 1, well, 1 and 1 are 2. So they just increase. So it comes up to 2 and down. It's the same shape. I'm sorry, this little dot should have been back at the 4. I'm not sure why it slid over, but it did. And the little dots are a little over too, aren't they? I'm so sorry. Everybody slid some. For total destructive interference, they're 180 degrees out of phase. Total destructive, 180 degrees out of phase. So where one goes up, the other comes down. And they just cancel. Total destructive, they cancel each other. And there's nothing there. Noise canceling headsets actually use total destructive interference. Partial destructive interference, you have them in phase, but I'm sorry, you have them out of phase. They'll be 180 degrees out of phase, but they have different amplitudes. So while one goes up and the other goes down, they don't do it by the same amount, and so they subtract a little. And we've got something that's smaller than the biggest one. And mixed interference, which is what real life is all about, you have different frequencies and different phase relationships, and you get sort of a hodgepodgey looking little thing. Let's stop with that and we'll do standing waves and resonance in the next video.